Hello, my name is Denis. I'm working as a deep learning researcher at Panasonic AI Lab in Mountain View. In this video, I will introduce our recent projects related to developing hardware-friendly deep neural network models for embedded computer vision applications. In particular, I was involved in developing embedded FPGA-based single-shot object detector for autonomous vehicles. First, I would like to overview Panasonic business areas. As you most likely know, Panasonic has a wide portfolio of consumer products like TVs, air conditioners, microwaves, cameras, etc. But other B2B businesses that are less visible to the public include solar panels, lithium batteries, avionics, car infotainment systems, security cameras, factory automation, and many other solutions. Computer vision plays an important role in many of those applications. In our project, the task was to build an autonomous commuter cockpit, like on these photos and video, and implement certain systems like battery, electrification, perception, planning, and control. Particularly, I was involved in perception subsystem. As you can see on the video, this vehicle potentially can transport passengers or deliver shipments at relatively low speed and automatically brake to avoid obstacles. This video presents relatively old prototype, while the new one is operated at Panasonic campus using service-on-demand phone application, and you can use that computer to transport around Panasonic campus. Modern perception systems are primarily deep neural network based, where around 4 cameras are usually used to capture 360-degree view around the vehicle for robust perception. Obviously, power consumption and hardware cost are very important for such systems in mass production. In this video, we recorded internal data for such 360-degree object detection perception. When we build an embedded object detector, several technical design choices have to be made. First, efficient detector model. For example, we can choose between two-stage detector or single-stage detector, or we can choose between some off-the-shelf backbone, or we can use optimized using neural architecture search backbone. Another important design choice is quantization scheme we use for our model. For example, it could be conventional floating point, which is not hardware friendly, or we can use integers like int8, or some other more like even lower number format like binary or ternary. Another important factor to consider is off-the-chip memory traffic, because most of the time this off-chip memory access time is the bottleneck for the inference speed. In the autonomous vehicle application, it's even more pronounced because the off-the-chip memory traffic will increase latency and also power consumption. Lastly, the hardware chip itself predefines trade-offs like power, latency, cost, programmability, etc. For example, custom ASIC chips would be the most power efficient and have the lowest latency, but may lack programmability, and development and manufacture costs will be very high. At the same time, off-the-shelf DSPs might be relatively cheap, but have higher latency and power consumption. In our case, we selected FPGA implementation as a prototyping platform that can be later extended to mass ASIC production. Of course, in ASIC you would have some programmable SoC with like complete computer vision pipeline and DNN accelerators as a final product. In this presentation, I will talk about 2 research projects related to DNN quantization and memory compression we accomplished. Then I will go through our developed FPGA-based hardware prototype for object detection. And lastly, as a bonus, I will present a project that deals with the challenges we faced when we applied our embedded prototype in real field trials. One of the most popular quantization schemes is conventional integer fixed point number representation that is widely used in many fields. Integer arithmetic is simple and it's power efficient compared to floating points. For example, Qualcomm hexagon DSP, adopted from signal processing to ML, uses integer representation. At the same time, schemes like binary ternary quantization that are showed on the pictures A and B are potentially even more power efficient at the expense of lower model representation capacity. Unfortunately, models with such representation are usually have to be retrained rather than fine-tuned, like in case of integers. In our paper, we propose a compromise method called ShiftCNN that quantizes model weights into n logarithm of 2 values, each of b bits. And each weight is basically a sum of this n log 2 values. So in case of n equal to 1, we arrive at non-uniform quantization as shown in figure C. As we increase n, we get closer to integer representation as shown in figure D. So the advantage of this scheme is that the arithmetic for such quantization is quite simple. So we have only adds and shifts. Therefore, this multiplierless method should be more power efficient than integers. But at the same time, it has more representation capacity than binary ternary numbers. In addition, because we have this kind of compromise, we can select n and b in a way that we don't even need to retrain a model from the scratch and just do fine-tuning like in integer case. One strong theoretical argument in favor of non-uniform types of quantization for CNNs is that is the commonly used weight prior during optimization. To be specific, this prior is usually Gaussian due to L2 regularization, which kind of naturally fits non-uniform quantization scheme. So in figure A, we show distribution of ResNet weights and batch norm parameters. As we can see, weights have Gaussian distribution due to regularization, while batch norms parameters are not. So in our experiments, we show that most of the image classification networks perform similarly to floating point when n equal to 2 shifts and b equal to 4 bits in our scheme, as shown in figure B and C. Again, for our ShiftCNN method, ALU performs only shift and add operations. In this slide, we can see on the left quantitative results of ShiftCNN quantization compared to base floating point format. Results on SqueezeNet, GoogleNet, and ResNet 18 prove that this n equal to 2, b equal to 4 works pretty much close to the floating point baselines without retraining. In the table to the right, we simulated power consumption on Xilinx FPGA, and then because ShiftCNN doesn't use multipliers, we can estimate that it consumes 4 times less power. When we optimize such architecture for ASIC implementation, we may even get probably better gains. Second research project I would like to present here is about feature map compression during model inference. The main motivation for this project is very high power consumption as well as latency when we go to off-chip DRAM memory compared to on-chip memory. Some experts estimate that the power penalty for going off-chip is approximately a factor of 100 in terms of power. So here we assume that the network parameters, weights, are already compressed using the efficient quantization scheme as we discussed before, And we are interested in compressing feature maps that could be quite large for high resolution image processing. Conventional methods deal with large feature maps using layer fusion, bottleneck layers, quantization, and sparsification. In addition to these methods, we further propose to compress already integer quantized features by projecting such integers into binary vector space and compressing such binary vectors further. Figure below shows the proposed compression-decompression layer that firstly binarizes integers into binary vectors. Second, we compress these binary vectors into lower dimensional vectors by exploiting bit-level representation redundancies using conventional convolutional layers. And then we basically keep only these compressed features in memory, while all the previous intermediate steps are processed by parts without kind of additional recomputations if we wisely select convolutional layers. Decompression steps are basically the reverse of the compression steps. So we take the compressed binary vectors, we project them back into original integer space, and this is how our method is working. Unlike ShiftCNN weight quantization, here we do bit plane compression that requires fine-tuning. And the main problem here is that quantization is not a differentiable operation. In our project, we used conventional straight-through gradient estimator with identity initialization of the compression weights. So figure schematically shows forward and backward passes for the binarization operation, which is a linear operation, and inverse of binarization. However, recent research showed that straight-through estimator is actually not the best estimator, and there are some more advanced methods like stochastic relaxation using like Gumbel softmax, and it should theoretically work better. So I think if we would use more advanced gradient estimator, we would get even better results and probably better stability for the fine-tuning process. Speaking of compression performance, we experimented with the single-shot SSD 512 object detector with the SqueezeNet backbone. We selected SqueezeNet backbone specifically because it already has kind of embedded compression-decompression bottleneck layers. And this way we can combine all possible methods to compress feature maps. So we can use layer fusion, quantization, and also on top of that we add bit plane compression using our method. We estimate feature map size for the first two network layers because they consume lion's portion of the memory due to large spatial dimension, which kind of obviously scale quadratically with the input height width dimension. Table at the bottom summarizes the fusion, quantization, and our compression results. In brief, our method gains a factor of 2 less memory consumption in addition to all the previous methods without any significant accuracy drop. Figure to the right compares types of compression decompression layers for our method. Usually this 2x2 convolutional layers with 2x downsampling, upsampling achieves the best performance complexity trade-off, and it's definitely outperforming like plain integer quantization if we just decrease number of bits to 6 or 4 bits. It's not going to be kind of working as good as when we do this bitplane compression, decompression. In this slide, I'm happy to show our developed FPGA-based prototype that runs SSD object detector at about 30 FPS under 15 watts with like 71% of mean average precision accuracy on Pascal VOC dataset. This is quite early prototype, so we have much later, better prototypes that run much faster. And actually, we already have some ASIC solution that can be used by the companies. So we've got our nice embedded object detector, and the question is, are we done? And unfortunately, the answer is no, because we cannot have 100% accurate model all the time, and this is very critical for the autonomous vehicle applications. Of course, we can try to tune model knobs to improve accuracy a bit, but usually it's not about the model itself. And most of the time in machine learning, the problem is in the dataset selection, which is critical to achieve target accuracy. So here we may talk about debugging tools, analyzing detector predictions for customers and ourselves, and we would like to present such work here. The main problem here is that DNNs are basically black boxes due to complex nonlinear models inside, and customers of such models would like to understand output predictions. So the main challenges here are: can we explain DNN predictions? Second, can we estimate certain explanation at a reasonable time? And the third, can we use the explanations to improve predictions? In our framework called Explain to Fix for object detection application, we are building an explanation model to address these challenges. So on the picture on the right, you can see that to the output of object detector, we add explanation model that generates special feature importance map, where the red color represents positive features and negative features represented as a blue color. And in case of object detector, we are generating this explanation for the particular class and particular bounding box. In our E2X framework, we propose to use backpropagation-based attribution method for object detection, and the advantages of this method are high fidelity explanations compared to state-of-the-art, and an order of magnitude higher computation efficiency to process large data sets on GPU clusters. We apply E2X to SSD 300 object detector and compare it to state-of-the-art explanation methods on these figures, and we can see that the speed is usually 10-20 times faster, and the correlation between our explanation and state-of-the-art is pretty high. Here we visually compare our E2X method to state-of-the-art methods like PDA, Lime, integrated gradients. In particular, here we see a bus, which is false negative because it is occluded by a car, and the car decreases confidence of the object detector, and we can see that our method correctly predicts positive red color features of the bus and the blue negative features of the car that occludes the bus. In the second example, we have a horse prediction, and the difficulty is that the horse has a rider, which is person class. So the most important horse features are head, legs, and tail. And interestingly, we can see that the tail here is confused with the person leg. To conclude, in this presentation, we presented hardware-efficient DNN quantization
scheme for embedded chips, our ShiftCNN method is approximately 4 times more power efficient compared to int8 integers. Second, we presented feature map compression method for on-chip processing with about 2 times memory drop on top of all prior methods. Then we presented our implementation of FPGA-based object detector that has a better power efficiency than GPUs and a much lower latency. And finally, I talked about explainability tool for DNN object detector to make your model transparent and accurate. Thank you. If you have any questions, please don't hesitate to ask me.